Hi, I'm BLSreekanth. I will be talking about real-world data analytics Redwine data midterm assignment today, and this is my student ID. So the agenda of this PPT is first to understand the raw data set and to visualize the data set and apply any transformations if required, and then do data normalization, and then come up with models that kind of predict the error measures, correlation coefficients, and find out the weights. And based on that we figure out what is the importance of the selected variables, and then we use those models for prediction, and we analyze the predicted results and see which one is the best model, and at the end we have references. So the first step is to understand the raw data set. The raw data set is called Redwine text, and it is a modified data version of Redwine samples taken from northern Portugal. It has around 1599 Redwine samples, and the data set has 5 input variables denoted as x1 to x5 and one target variable y, which maps to the quality of the red wine. X1 to x5 map to citric acid, chlorides, total sulfur dioxide, pH, and alcohol. So first we load the text data into data frame and we read the data. So the data doesn't have any headers. So what we do is while loading we also specify strings as factor to ensure that the character data is not converted to factors. Then we assign the column names to column names, and then we use lapply as numeric to ensure that all the columns and the data in the columns is converted to numeric. Then we use isFinite to ensure that the data doesn't has any invalid values. So if there are any invalid values, it throws an error message. So here is the output of the first few rows of the data set. Then Redwine data is again converted to a matrix, and the first 6 rows of the matrix are printed. So you can see here it is being converted to matrix, and the first 6 rows of it are being displayed. So for displaying the first 6 rows we use this printf function, and then we save the file as an RDS file. We also so this is the output of the code that is displayed here. We can see the matrix dimensions 1599 rows and 6 columns, and the matrix is saved. So we use so I use my student ID for seeding. This is to ensure reproducibility for all the data operations that we do and consistency in that. So we create a subset of Redwine data, and then we print the subset dimensions here. So you can see that subset has only 400 rows and 6 columns. Now we have to do data visualization here. So we come up with predictors and targets. So predictors are all the first 5 columns of the data, and the target is nothing but the quality column. Then we plot graphs. We try to visualize the relationship between the variables using scatter plots and histograms. So for scatter plots we use plot, and for histograms we use hist, and we use a PDF function to capture all these graphs into a single PDF file. And once the graphs are copied to that file, then we close that PDF device using devoff. So we look into the scatter plots of the PDF file, and then we try to find out the correlation, if there is any correlation between these variables, predicted variables, and the target variable. So we can see that for chlorides and sulfur dioxide there is very less correlation or negative correlation. So when the values of chlorides and the sulfur dioxide are low, the values of the quality are high, and the values of pH, it is uniformly distributed. So it has very little correlation with quality. And the values of alcohol, if they are high, the quality of wine is also high. So it has strong positive correlation. And if you look at the scatter plot of citric acid and quality, so citric acid might have very less or weak correlation because the data points are distributed across all the quality levels. Next we examine the histogram. So from the histogram we can see that except pH, most of the variables are rightly skewed. Some are highly positively skewed, and some are moderately skewed. And the distribution of quality we can see is that it is kind of multimodal or bimodal distribution. Next, what we do is we create correlation between the predictors, and then we also try to plot that correlation in the form of a correlation matrix. You can see the correlation matrix, and then we try to calculate correlation between predictors and quality, and we display that correlation with quality. So the output says here, so correlation within the predictors and among the predictors, and correlation between each predictor and quality. We can see that alcohol has high correlation, chlorides and total sulfur dioxide have negative correlation, and pH has very minimal correlation. So now we have to do transformation. So for transformation, we select 4 predictor variables: so citric acid, chlorides, total sulfur dioxide and alcohol, and we drop pH because it has very weak correlation with quality. And we use 3 different functions: min max normalization, log transform, polynomial transform. We use E107 package of R, which is basically used for classification and regression. And in this case, we use the skewness function of E107 package to determine the skewness value, and based on the skewness value, we do different types of transformation on these variables. For example, if the skewness value is greater than 1, we apply log transform. If it is between 0.5 and less than or equal to 1, we use polynomial transformation. If the value is less than or equal to 0.5 and greater than or equal to minus 0.5, we use min max normalization. Else we don't do any kind of transformation. We leave the variable unchanged. So for the transformation, we are selecting only 4 variables here: citric acid, chlorides, total sulfur dioxide and alcohol. We are skipping pH because it doesn't have any, or it has very weak correlation with quality. And this is the code for that, and you can see the output here. So once the transformation is done, we have to apply normalization. So for normalization, we again check if the variables are already normalized. If not, then we do min max normalization for the predictor variables. Now once the predictor variables are normalized, then we apply normalization for the target variable also, and then convert the data into matrix and display the first 6 rows or first few rows. And after that, we save that file. We save the transformed file to a text file. We skip the row numbers and save with the columns. So normalization is required because we need to ensure that all the variables are scaled to compare them appropriately. And once normalization is done, then we have to come up with different models. So in this case, we use agva fit 718R file. We import it and load it into our workspace. We use different aggregation functions and fitting aggregation models of it, such as AM, GM, PM, and QM, and weighted arithmetic mean, weighted power means, ordered weighted average, and weighted quasi-arithmetic means. So what we do is, first we import the transform text into our data frame, and then ensure all the columns of it are numeric, and then print the structure of the data frame. So this is the structure of the data frame, and then we invoke the fit.quam function in the agva fit 718R with the data transformed copy, and we specify the output file. And output file, this is basically for capturing the weights, and the status file for capturing the compute stats such as RMSE, RME. And we also specify the aggregation functions like arithmetic mean, or inverse aggregation functions like inverse aggregation, inverse arithmetic mean in this case. And we read the lines of the stats file and display them as output. So we do this for all the weighted arithmetic mean and weighted power mean with p is equal to 0.5. So we can see the output here that displays all the errors and error measures and weights. Similarly, we do it here for the weighted power mean with the p equal to 2. And before doing it for OWA, we transform the data set to a matrix and then pass it to the OWA function, and then display the output. So we have two tables, one with error measures and correlation coefficients, and the other one with weights and parameters. The first table is displayed here, where each model RMSE data, MAE, Pearson correlation and Spearman correlation is displayed. So for WPMP equal to 2, we have best Pearson correlation and Spearman correlation values, whereas for OWA model, we have lowest RMSE and MAE values. And if you look at the weights and parameters table, WPMP equal to 2, it has higher weights for variable 4, and we have displayed the weights for all the 4 models here. Different data sets use aggregation functions and inverse functions. So importance of selected variables. So based on the data that we have already, alcohol has the highest significance impact on the target variable, and total sulfur dioxide has a moderate influence on the quality of the wine. The remaining two variables, citric acid and chlorides, have very negligible or minimal impact on the quality of the wine. And we use these models for predicting the quality of wine for the new data set. So we have the new data new input. In this new input also we apply similar kind of logic that we did in the earlier. We drop 3.53 because that correlates to pH, so we are excluding that value here, and we applied the column names, and then we try to calculate the min-max values of all these columns, and then we print those values. Then we apply log run. Again, we calculate the skewness based on E107 skewness function and check the skewness value. And based on the skewness, again we do a similar kind of transformation for all these new input. Once the transformation is done, again we do normalization and we print that normalization data. The normalized data is again converted to a data frame, and we also compute the min-max values of the target variable and display it here. So this is the output for it. And then we create a list of weights. So all the weights that we have received with 4 models, we create a weight list, and then we use a loop to figure out the weight name, and then pass that based on the weight name we pass the respective weights to the QAM function and the normalized input. We pass the normalized input and the weights, and then we get the predicted normalized output. And the predicted normalized output, again we do reverse normalization to get the original scale of the quality, and then we finally print the best model that has the weights, and the best model for best model weights name and the decimal and integer values of that quality. So here we have the models that are applied, and we can see the predicted values in decimal and integer, and we can see that WPMP2 provides the highest quality of the product of the target variable. So we consider WPMP2 as the best fitting function because it provides the highest predicted value. Not only that, it emphasizes larger values in the data due to quadratic transformation, and this is appropriate for data sets where higher values are given stronger preference, or they are allowed to influence the target variable strongly. And the best conditions to achieve high quality of wine is to have high level of alcohol and moderate content of total sulfur dioxide and very reduced or minimal content of citric acid and chlorides. And implications are, so this model is sensitive to larger values, and it is effective for non-linear relationships. Limitations are its overemphasis on larger values can underpredict or underestimate the contribution of smaller variables. and there is always a chance of overfitting because the emphasis is high on the larger values. And these are the references. Thank you.